Okay, so uh, right, this thing you see over here, this is Project Euler, and I mean I've just started on it. I spent a week and I've solved 50 questions. Um, that's how I got this award. Solve 50 consecutive problems. I've done that. Actually, I've solved 54 out of 844. So there are 4 extra problems that I've solved, which will link to some other problems. And yeah, so now I'm at level 2. Right, so why am I making this video? You would have noticed that I was gone, as in I wasn't putting any videos for, I guess, a month, you could say. Right, so there was a lot of stuff happening in my life, and this is one of those things, right? This is like just something I was doing for practice. And let me just show you the progress I've made. So as you can see, 50 problems solved, and it's not just these problems that I've solved that I want to show to you. I actually want to show to you some functions that I've made that make my job easier. Oh right, these are the recent problems that I was working on. So this was the 50th problem, which was about like primes, consecutive primes adding up to another prime or something like that. So you have to kind of think about it a little bit to go from order n squared to order n log n algorithms, something like that. So those are the kind of problems these are. So if you are new to Project Euler, Project Euler is basically a site where you see problems which are based on either computation or mathematics. And by mathematics I mean number theory and inequalities. I haven't seen anything related to other fields of mathematics till now. Mostly it's just number theory, and it's not even that complicated of number theory. Sometimes it does get complicated. I mean, you can make it complicated if you want to do some something in the fastest way possible or something like that. For example, problem 48, that was something that I complicated for no reason, just to show that I can do it in a better way. That's why I did it. So you had to find the last 10 digits of this series, which is basically just finding out what this sum is modulo 10 power 10. So the way I did that is using these functions. So one of this is fast exponentiation. So in general, whenever you exponentiate something, so let's say you want to find 2 power 10, it doesn't just iterate 10 times and then do 2 times 2 times. No, it doesn't do that. Instead, the way your computer handles it is using another method, which is way better, right? So instead of 10, it does it in 10 log, not 10 log, okay, it's log 10, right? So it's in log 10 time, log base 2 in this case. The way it does it is by squaring instead of just multiplying, right? So say you have x as your base, then you just square that, you get x square, and then you get x power 4 and so on. So once you get all of these spherical powers whatever it's called, you can multiply these based on whether or not the exponent has a 0 at a certain place in its binary expansion. Why am I even telling you about all of this? Yeah, it's not important, but yeah, this is like one of the things that I had to make, and I modified this by taking the modulo with respect to whatever modulo you will have, and that means that I can now use this to get x power n modulo m pretty fast. Yeah, and right, which helped me. I mean, this went from order n to something like, not order n, it was like order n square. Yeah, order n square to something like order n log n, or even better, because you have other things like totient, Euler totient, and solving in different what do you call it, modulos. Yeah, and then combining using the Chinese remainder theorem, something like that. So I even made functions for those. Right, so what I want to show you is not these problems. There are 50 of these. It will take too long for me to show everything, although I could show some good problems that I think were nice in the end. No, what I want to show you are all the functions that I've made. So these are, there's a lot of them. So these are all the functions that I've made while solving these 50 problems. Let's just go through these. First is LC for GCD AB. So how Euclid's division works, right? Well, you can use Euclid's division to get the GCD, but you can also use the Euclid's division to get the GCD as a linear combination of the two numbers you gave in, right? So instead of just getting the GCD, what you could do is also return the coefficients for those for that linear combination, and that's what this thing does. So for example, oh, and this is not the original function that I wrote. The original function also had some print statements, which was more descriptive and everything, but then yeah, that's just the way it is, right? So let me just try to print something. So print LC for GCD, what should I say, what should I input in this, A and B? I just choose any two co-prime numbers. That's gonna give you 1 as a GCD. So I don't know, 24 and 35. Now okay, that's not co-prime. Actually it is, it's just 4 times 50 times 5 times. Yeah, so that's nice. So if I just print that, it will give me a tuple, negative 16, 11 and 1. What these numbers are is basically, if you do negative 16 times 24 plus 11 times 35, that will give you 1. So it has written 1 as a linear combination of 24 and 35. And there's this whole number theory thing where you can write the GCD as a linear combination of these numbers every single time, and this function working shows that yeah, that's actually true. It even has a name, it's a theorem, I don't remember it, but anyway, so it's pretty provable by using Euclid's division, right? Yeah, so that's one function I made. Then you have the GCD function, the usual GCD function, and yeah, that's pretty easy because during Euclid's division you will get G, right? So you can just return that as a G or D or whatever you want to call it. See, since you get the GCD, just return that, right? So my GCD function is just that, relies on Euclid's division, gets the GCD, and yeah, that's pretty much it. And yeah, Euclid's division is like order log n something, right? Yeah, so if both of them are order n, if both A and B are order n, then this will be order log n, right? Then you have the LCM, which is just A times B upon GCD of A and B, so that's pretty easy. You have this DIO function. It's short for the Diophantine solutions. So let's say you have the equation x times of A plus y times of B equal to C, but you have the restrictions that x and y must be integers, and of course A, B, C are integers. Then how do you get at least a solution of that? Because once you get one solution, you can use some stuff from number theory to generate all of the solutions. Of course there are infinite solutions for this, but yeah, so how do you get a solution of this? The way would be to first of all figure out if it is actually having a solution, which is if C is divisible by the GCD of A and B, and once it is, in that case just divide everything by that GCD, and then it basically becomes like x times of A plus y times of B equal to 1, something like that. 1, or something that is like an integer because now the GCD is 1. So yeah, right. And then what you can do is just write 1 as a linear combination of A and B and multiply by whatever the reduced C is, right? So x and y you get, just multiply by C, the reduced C of course, and that will be one solution. And then you can reduce that further, you can change that solution a bit so that it becomes a nicer solution and follows some criteria, but whatever, that's not a big deal. So this is all coded like that, right? You just use the previous function that you made to get x and y, then you just divide divide A and B by your GCD. You also divide C by GCD and multiply by x and y to get the x and y for not 1 but instead C by G, right? Yeah, and once you have that, you can do some reduction on that. just search Diophantine equations, linear Diophantine equations, and you will get this whole theory. But yeah, so that's about this function. Next we have CRT. It solves the Chinese remainder theorem. Yeah, so Chinese remainder theorem is basically if you have two co-primes P1 and P2, and some number x is congruent to R1 modulo P1 and R2 modulo P2, then what is it congruent to modulo P1 times P2, right? To do that, you would have to do r1 plus some integer times p1 and r2 plus some integer times p2, both being the same thing, and then you can just combine these, because if p1 divides something and p2 divides something, then p1 times p2 divides something, since they are both co-prime, right? So the basic thing it boils down to, once again, is just a linear Diophantine equation. So that's why I made this dio function, so that you can use it for the CRT. So it's basically just this. It's pretty small, really, isn't it? Yeah. PF is its prime factorization. So given a number, it returns a dictionary containing all the prime factors of this guy and their powers in its prime factorization. Sig is just using this PF to get the sum of all the divisors of of n. Generate primes is basically just the that guy's name is hard to pronounce. It's the prime sieve algorithm. Yeah, I'm not gonna pronounce that name. You can search up what that name is, but it's the prime sieve algorithm, which generates all the primes till n. Yep. Right. It's like order n log n, I think. Yep. Oh no, wait, it's order n log of n, because 1 by 2 plus 1 by 3. Yeah, that thing is log of n, something like that. Anyway, fast s. Yeah, so this function I just explained. I won't explain it again. Multiples, it returns all the multiples in a certain range of some certain number. So L is a list containing a lower number and a higher number, and M is just some number, some divisor, and it just returns all the multiples. And I'm not gonna show the code for that, because I mean, this, okay, we just show it. It's pretty trivial. So yeah, div by all, that is basically going to give you a list of numbers in range. Well, okay, it's kind of hard, because this was based on a certain question that I was solving, so it's kind of too specific. But basically, say you have all the multiples of 2, so the first 100 multiples of 2, not all, of course, that would be infinite. You have the first 100 multiples of 3, the first 100 multiples of 5, and now you want the union of all these sets. How do you do that? So you want something like first of all, using inclusion exclusion, for that you would require some kind of intersection of all these sets. So div by all basically gives an intersection of these sets. Yeah. And this function, which I have very lazily named 1, I should really name it as div by 1 or div by any 1. This is the union of those sets. And subset, okay, so I ordered them in the wrong way, but yeah, this is from some other question completely. So it just gives us subsets of range n, which is 0 till n, I think it was 1 till n. Yeah, so 1 till n inclusive both. So that range of integers, of course, 1 2 3 4 till n, it gives us the subsets of these. So 2 power n subsets, you know that. It generates all of those. All right. Is prime just a prime checking function. I've done the square root stuff, that optimization. Also done that even and odd stuff, like, yeah. Okay, is left truncable. So truncable primes are primes such that, okay, let's not go for truncable primes, let's first go for left truncable primes. So left truncable primes are primes such that if you remove digits from the left in their base 10 representation, if you remove the digits from the left side, then the remaining numbers, those still form a prime, and you can keep doing that, and it will eventually still be prime all the way till 1 digit. And yeah, those are just truncable, left truncable primes. There are right truncable primes as well, and the weird thing is these are only a certain number of these primes are there in the world. We haven't found more right truncable primes, or I guess you can't find more right truncable primes or more left truncable primes, which also means that both side truncable primes are also fixed in number. And so that was one of the questions, find all of these and do something with them. I don't remember it exactly. Okay, oh yeah, this thing. So it generates an increasing sequence, kind of like what you get in star bar theorem. So you got 1 1 1, then 2 2 2, 3 3, something like that. So you have low and high. So the sequence is like every digit of this every character of that sequence, and yeah, I should say that is between low and high, and size is the size of the sequence, of course. And this basically uses the star bar theorem or something like that. Yeah, so it just generates a sequence that follows these criteria, that it's going to be increasing, or in this particular case non-decreasing, it should be a better word. Every single character is between low and high, and yeah, that's pretty much it actually. So you might think it's like pretty trivial to generate these, but actually it is kind of trivial as well, but still you have to put some thought in it. It's kind of like a recursion or something. Okay, perm is just creating all the permutations of a certain string. So if your string is like of 10 characters, it will give you all the 10 p5 permutations by permitting a string into a string of 5 characters. And you can change this number, of course. You change the value of stop, you give that extra parameter, it will tell you, it will give you the permutations of that length. So yeah, that's perm of some string. Circ of string is just all the circulations of the string. So just rotate the string, remove one character from the last and put it on the top, something like that. That gives you that. Yeah, this is just for utility. This wasn't like really useful in a more algorithmic way. It's just for utility to make my code simpler to read. Okay, primitive right triangles. This generates all primitive right triangles with a certain parameter p. And yes, this is kind of big. I mean, look at this. So look at this weird thing. This is actually the formula to generate these primitive right triangles, and all I'm doing is just doing 2 for loops and figuring out all primitive right triangles which have this parameter, which is pretty basic algorithm, nothing too complicated. Okay, factors of n. It gives all the factors of n. Pretty obvious. This uses the prime factorization that we already used. We wrote that last time, something like that. Okay, what is this thing? Right triangles p. So this is something that relies on recursion, and it gives you all the right triangles with a certain parameter p, not just primitive right triangles. This is its code. Wait, should I be showing these codes? I don't know. Anyway, then this function is just to it's kind of a utility function. It just checks if certain number is a pentagonal number. You can read about pentagonal numbers on Wikipedia or whatever, but yeah, these are all the functions that I've generated for the first 50. And of course I couldn't include all the methods that I've used to solve the 50 questions, but I have in fact made some comments on my forums, I think. Oh wait, I can't be showing these answers. No, wait, I mean, okay, first 100 I can show, I should not show. That was the thing. Just go back to the progress thing. But yeah, so I commented on a lot of these later questions. That was nice experience. Like some of these I solved better than what other people were doing. People were doing like n square algorithms. I was doing n log n algorithms. People were doing some weird computational thing which does not involve a lot of maths. I was doing something that does involve a lot of math and relies less on computation. And so this was like a nice journey. Yep. Right, why am I making this video now that I have solved only 50 questions? You might think that I would have solved 100 questions and then I would make this video. Well, I want to take a break. Honestly, it's kind of taxing to be solving 1 or 2 questions each day, considering my kind of unhealthy routine with a lot of stuff going on each day. I can't be giving this much of time to just solving these problems, which are sometimes not that satisfying. I mean, they are, of course, in general they are satisfying, but sometimes don't you just feel that, oh, these are not that satisfying. But yeah, and about this username, I don't know, I just thought put something, so I basically put my email in there. Yeah, that's it. That's where the video ends. I'll see you guys next video. Bye.